On October 26, 2022, astronomers pointed the James Webb Space Telescope at a routine deep field survey, and what came back made several of them stop and rerun their own calculations, convinced they'd made a mistake. A tiny, unremarkable-looking object, barely a smudge among thousands of faint points of light, turned out to be a fully formed galaxy sitting at a distance that placed it just 290 million years after the Big Bang. Not a faint primitive cloud of newborn stars, which is exactly what every model of the early universe predicted astronomers should find at that age. A structured, massive, surprisingly mature galaxy, sitting where, according to decades of established cosmology, nothing that developed should have existed yet. That single discovery turned out to be the first thread in what's become one of the most genuinely contested debates in modern astrophysics, a debate serious cosmologists are still fighting over right now in 2026. Stay with me, because what James Webb has actually found, and what leading physicists are honestly saying about it, is stranger and more scientifically consequential than any single headline can capture. Let's start with the object that started it all, because the story only makes sense once you understand exactly how surprising it was. That galaxy, eventually cataloged and studied intensively by teams around the world, showed a redshift so extreme that its distance wasn't in question. Spectroscopy confirmed it decisively. What was in question was its structure. According to the standard model of cosmology, the framework virtually every astrophysicist has worked from for decades, called lambda CDM. Galaxies at that early stage of cosmic history should still be small, chaotic, and just beginning to assemble out of clouds of primordial hydrogen and helium. Instead, this object looked disturbingly organized and disturbingly bright for something that young, and it wasn't alone for long. By 2023, Webb's deep field surveys had turned up an entire population of similarly puzzling objects, compact, extremely luminous, points of light that astronomers eventually nicknamed little red dots, a term that's stuck in the scientific literature specifically because nobody has fully agreed on what these objects actually are. Some researchers believe they represent impossibly massive, impossibly compact early galaxies. Others argue they're active galactic nuclei, meaning supermassive black. Holes feeding aggressively enough that the surrounding material glows intensely from a very small region of space. A newer, stranger possibility has entered the conversation more recently still, the idea that some of these objects might be something in between, a category some researchers have started informally calling black hole stars, a classification that simply didn't exist. In astrophysics, textbooks even a few years ago, whichever explanation eventually wins out, and the scientific community genuinely hasn't settled this yet, every single option on the table creates real problems for models that were considered settled science before Webb launched. Here's where the numbers get genuinely uncomfortable for cosmologists. A study analyzing Webb's deep field data identified 87 candidate galaxies that appear to have formed somewhere between roughly 200 and 400 million years after the Big Bang, a number that, if even a meaningful fraction of those candidates hold up under further scrutiny, sits in real tension with what lambda CDM predicts should be possible in that narrow window of cosmic time. Researchers involved in identifying these candidates have been notably careful in how they've framed the implications, several stressing publicly that if even a modest portion of these objects are confirmed as genuine structured galaxies, rather than statistical flukes or misidentified foreground objects, the standard timeline for how quickly galaxies can form and grow needs serious re-examination. And this is exactly the tension that makes this such a genuinely fascinating scientific moment rather than a settled conclusion, in either direction. Because for every astronomer arguing these objects represent a real crisis in cosmology, there are equally credentialed researchers arguing the explanation is less dramatic, that early star formation may simply have been more efficient, more rapid, and less linear than older models assumed, without requiring any fundamental rewrite of the Big Bang itself. That argument, playing out in peer-reviewed journals, at conferences, and increasingly in public interviews throughout 2025 and into 2026, is the real story here. A genuine, high-stakes scientific fight over how much of our understanding of the universe's first billion years actually needs to change. Let's actually dig into the number that caused so much alarm in the first place, because it tells you everything about how real science handles a claim this explosive. In 2023, astrophysicist Michael Boylan-Colchin published an analysis showing that some of the brightest early galaxies Webb had identified appeared to require converting nearly 100% of their available gas directly into stars, an efficiency so extreme it would break a rule considered close to sacred in astrophysics. In galaxies we observe nearby, in our own cosmic neighborhood, that efficiency typically sits somewhere between 1 and 10%. Gas doesn't simply collapse into stars instantly and completely. It needs time to cool, to fragment, to go through cycles of intense star formation followed by quieter periods called quenching, before settling into anything resembling the stable galaxies we see today. A galaxy converting all of its material into stars in one shot genuinely would represent something astrophysics couldn't explain. Here's where the real story gets more interesting than the initial headline, and this is the part competing narratives tend to skip entirely. Scientists didn't just accept that terrifying 100% figure and move on to writing eulogies for the Big Bang. They did what good science is supposed to do. They went back and checked it, rigorously, repeatedly, using different methods and different data sets. And what they found mattered enormously. A team led by Katherine Chorowski, publishing follow-up analysis in 2023 and 2024, identified a major source of contamination, skewing the original brightness measurements: active galactic nuclei, meaning supermassive black holes actively feeding at the centers of some of these galaxies, adding extra light that made the galaxies appear significantly more massive and therefore more star-efficient than they actually were. Once that contamination was properly accounted for, the star formation efficiency estimate for the most extreme cases dropped substantially, down to roughly 30 to 40% according to that follow-up work. Now, before you assume that resolves the whole controversy, it doesn't, and this is exactly why the debate is still alive in 2026 rather than settled. Even at 30 to 40%, that's still 3 to 4 times higher than the star formation efficiency astronomers observe in typical galaxies today, still representing a genuine unresolved tension with pre-Webb theoretical models, just a meaningfully less catastrophic one than the original 100% figure implied. Researchers across multiple teams throughout 2024 and 2025 have proposed a range of explanations for that remaining gap. Everything from the idea that early star-forming environments naturally reach much higher gas densities than anything we see nearby, since primordial gas cools less efficiently at lower metal content, driving up star formation efficiency as a natural consequence of early universe chemistry, to the possibility that early stars formed in a completely different mass distribution than stars do today, weighted more heavily toward larger, brighter stars that would make a galaxy appear more massive and luminous for the same actual amount of star formation. This is what a genuine, functioning scientific process actually looks like, and it's considerably more interesting than a simple story about physics breaking overnight. An alarming initial number gets published, other teams immediately scrutinize it, using independent data and independent methods. A significant chunk of the anomaly turns out to be an observational artifact, specifically light contamination from feeding black holes that hadn't been properly separated out. But a smaller, still genuinely unexplained tension remains, and multiple serious research groups are actively working through different physical explanations for it right now, none of which require abandoning the Big Bang or rewriting the age of the universe. That pattern, an eye-catching initial anomaly, rigorous independent follow-up, partial resolution, and a smaller remaining puzzle that keeps researchers genuinely working, has actually repeated itself across several of Webb's most famous early universe surprises. The broader excess of massive galaxies at redshifts between roughly 5 and 9, meaning galaxies, existing when the universe was between about 600 million and just over 1 billion years old, has been documented across multiple independent research teams and multiple separate survey programs, and it has not fully gone away the way the star formation efficiency crisis partially did. Recent work combining large area JWST survey programs throughout 2024 and 2025 has continued, finding number densities of massive galaxies that exceed what pre-Webb theoretical models predicted, even after properly accounting for contamination from active galactic nuclei and other known sources of measurement error. That remaining excess is real. It's been confirmed by multiple independent groups using different survey data, and it still requires either a moderately enhanced star formation efficiency in the early universe, some adjustment to how the standard cosmological model handles this specific era, or some combination of both. A genuinely open, actively researched question rather than a settled crisis or a settled non-issue. Now let's address one of the more dramatic sounding claims that circulates around this topic, because it's a genuine feature of cosmology, not some undiscovered flaw in physics, and untangling it actually makes the real science more fascinating, not less. It's true that Webb has observed galaxies that, according to standard cosmological models, are currently receding from us faster than the speed of light. That sounds like it should be impossible, and if you're picturing objects physically moving through space faster than light, it would be. But that's not actually what's happening, and this is where a real, well-established piece of cosmology gets misrepresented as some kind of impossible paradox. The key distinction is this: special relativity, the theory that says nothing can travel through space faster than light, governs motion within space. It doesn't govern the expansion of space itself. In an expanding universe, the space between two distant points can stretch at a rate that causes their separation to increase faster than light speed, without either point actually moving through its own local region of space any faster than light. This isn't some fringe idea invoked to paper over an inconvenient discovery. It's a foundational, decades-old, well-understood feature of general relativity, and cosmologists have built detailed models of exactly why light from objects beyond what's called the Hubble sphere, the boundary at which recession speed due to cosmic expansion equals the speed of light, can still eventually reach us. Light emitted early enough, when that boundary was different, can still be traveling toward us even as the space it's crossing continues to stretch, arriving billions of years later carrying information from a boundary that has since moved. It's a subtle, mathematically well-worked-out consequence of cosmic expansion, not evidence that Webb has broken relativity or exposed some fundamental flaw in how space works. That said, and this is worth being honest about, there genuinely are aspects of early universe cosmology where serious researchers are proposing real modifications to the standard model, and it would be dishonest to pretend otherwise. The tension around excess numbers of massive early galaxies has prompted legitimate theoretical work, exploring ideas like early dark energy, a hypothetical, temporary boost to the universe's expansion rate in its first few 100,000 years that could help reconcile some of these measurements, alongside more conservative astrophysical explanations focused purely on star formation physics, rather than any change to cosmology itself. Both categories of explanation remain active areas of publication and debate through 2025 and into 2026, and neither has definitively won out over the other yet. These compact, extremely luminous objects, discovered scattered throughout Webb's deep field images, still don't have a single settled explanation the broader astronomical community fully agrees on. Research published across 2024 and 2025 has increasingly pointed toward active galactic nuclei, feeding supermassive black holes, as the leading explanation for at least a substantial portion of this population. Work led by researchers, including Jorrit Matthey and Jenny Green, has found spectroscopic signatures consistent with rapidly accreting black holes at the centers of many of these objects. But even that explanation raises its own follow-up mystery, because if these are indeed feeding black holes, some of them appear to be growing far faster and reaching far larger masses at far earlier cosmic times than standard models of black hole formation. And growth comfortably allow for reopening a version of the same too big, too soon problem in a different form. This is genuinely what it looks like when a powerful new instrument outpaces the theories built to interpret it, and it's a situation astronomy has actually faced before, when larger, more sensitive telescopes and surveys have come online throughout history. They've regularly turned up populations of objects that didn't fit existing categories at first, forcing genuine revisions to established theory rather than wholesale abandonment of it. What makes Webb's current moment particularly significant isn't that it's proven the Big Bang wrong. No credible mainstream cosmologist working with this data is arguing that. It's that Webb has revealed the first several hundred million years of cosmic history to be considerably more active, more efficient at producing massive structure, and more complicated than the simplified models astronomers were working from before launch, and pinning down exactly why is now one of the most actively contested, well-funded research questions in modern astrophysics. So where does that actually leave the story, honestly, standing here in the middle of 2026, looking at everything Webb has turned up since that first surprising galaxy back in 2022? Not with the Big Bang model shattered, and not with nothing to see here either. Something considerably more interesting than either extreme, a real evolving scientific fight over exactly how much of our picture of the early universe needs updating, playing out in public, in peer-reviewed journals, among researchers who fundamentally disagree with each other and are saying so, by name, in print. Let's connect the full arc of this story one more time, because it's genuinely more compelling laid out honestly than any manufactured crisis narrative could make it. Webb found a fully structured galaxy at just 290 million years after the Big Bang, a genuine surprise that kicked off years of intensive follow-up study. It found a population of massive, unexpectedly abundant galaxies at redshifts corresponding to the universe's first billion years, a tension that's been confirmed, refined, and partially explained across multiple independent survey teams, but that still hasn't fully resolved even after careful correction for observational contamination. It found galaxies that initially appeared to convert essentially all of their gas into stars at once, a claim that triggered real alarm in 2023, was substantially walked back once researchers identified active galactic nuclei skewing the original brightness measurements, and settled into a smaller, still unexplained excess that multiple teams are actively working to explain through legitimate astrophysical mechanisms rather than any rewrite of cosmology itself. And It found little red dots, a genuinely unresolved population of compact, luminous objects that most current research increasingly attributes to actively feeding black holes. Though even that explanation opens its own follow-up puzzle about how those black holes got so massive so quickly. None of that requires abandoning the Big Bang, and no serious, credentialed cosmologist working with this actual data is arguing that it does. What it does require, and what's genuinely been happening in real time since 2022, is careful, contested, occasionally messy scientific revision, exactly the kind of process that produced every major advance in physics over the last century. Early, dramatic claims get published. Independent teams scrutinize them using different methods and different data. Some anomalies turn out to be measurement artifacts. Others turn out to be real and force genuine updates to how astrophysicists model star formation, black hole growth, and the earliest stages of galaxy assembly. That's not a story about physics being destroyed. That's a story about physics actually working under real pressure from real, previously unavailable data. And here's why this should still genuinely excite you, rather than needing an invented apocalyptic framing to feel important. This isn't a closed case. Webb's science operations are expected to continue for another decade or more, given its current fuel reserves, meaning the population of these puzzling early galaxies, little red dots, and unexpectedly massive structures is only going to grow as more deep field surveys complete. Meanwhile, upcoming instruments are specifically positioned to help settle these exact questions. The Vera C. Rubin Observatory, now conducting its full 10-year sky survey from Chile, will help refine statistical samples at slightly lower redshifts. And the European Space Agency's Euclid mission, already returning data throughout 2025 and 2026, is specifically designed to survey enormous volumes of sky at the depth needed to catch far more of these early massive galaxies, giving researchers the larger statistical samples needed to finally determine how much of this remaining tension reflects genuine new astrophysics, and how much will eventually resolve the same way the original 100% star formation efficiency scare did, through more careful measurement, rather than a fundamentally broken universe. So here's what I want to leave you with. James Webb hasn't shattered the Big Bang, and it hasn't proven the universe had no beginning. What it has done is force some of the smartest, most experienced cosmologists working today to admit openly in published papers with their own names attached that the first several hundred million years of cosmic history were messier, faster, and more efficient at building massive structure than anyone predicted before this telescope launched. That's a genuinely remarkable scientific moment, and it's still actively unfolding. Do you think the remaining tension gets fully explained by better astrophysics, more efficient early star formation, bigger black holes forming faster than we assumed? Or do you think there's still a real crack in the standard cosmological model that hasn't fully revealed itself yet? Tell me what you think in the comments, because new survey data from Rubin and Euclid is landing constantly, and I'll be here breaking down exactly what it means as it arrives. Subscribe and turn on notifications, because the next major update to this story could come sooner than you think.